Hi, Mr. T here. In this video we're going to look at the photoelectric effect. So in this first slide here we've got a picture of a photoelectric cell. The photoelectric cell consists of an emitter and a collector and a glass surround. Now inside this whole apparatus there is a vacuum, there's no particles, they've all been removed. The surround is glass so that the light can travel through it without being impeded. So the light photons hit the emitter surface, the inside of this surface, and when they hit the surface, they cause electrons to be pushed off or to be emitted. This emitter is a concave shape, so the electrons, when they're pushed off, are directed towards the collector. Now this production of these electrons going towards the collector are then able to go all the way round back to this emitter again. So this is an anode and this is a cathode, and this produces an electric current when this happens. Now during this video I'm going to use these constants at the top, Planck's constants, the speed of light and a charge of an electron. If you need to go back and refer to them, just pop back to this part of the video. These are the equations that we need to know for working with photoelectric cell problems as well. And there we go, there's the electrons being emitted. So the photoelectric effect, if we look closely at the emitter, it's just a piece of metal called an emission plate, a nice shiny piece of metal. So we know that metal has these delocalized electrons sitting on top. If the light rays, or individually called photons, hit the surface of this emission plate, they can dislodge the electrons and push them off. Once the electrons have been pushed off, they have a certain amount of kinetic energy. We can calculate any light ray we're coming in has either a wavelength or we can find out its frequency. So we can just use the wave equation to change between wavelength and frequency. Often we use frequency when we're doing further calculations. To find the frequency, we just divide the speed of light by the wavelength. If you have a higher frequency hit the plate, you will get electrons emitted with more kinetic energy. The opposite's true. So if we have a lower frequency, so here we have a bigger wavelength, 500 instead of 400 nanometers. So now it has a lower frequency. The lower frequency hits this emission plate, then the electrons are popped off with less kinetic energy. So if the light that hits the plate but if the light that hits the plate is too low, no electrons will be emitted. So in this case now we've got down to red light, 600 nanometers. It has a smaller frequency again, but now the frequency is so small that instead of electrons being emitted, the light is just reflected off. Now the point at which the frequency just is able to pop the electron off, and the electrons have no kinetic energy, this is called the threshold frequency. Any light that has a frequency that is less than the threshold frequency will not be able to eject the electrons. Okay, so if I was to hit a plate with a low intensity light or a dim light, not many photons, I would get a very few electrons off, but they would still have the full amount of kinetic energy. If I was to increase the intensity, if I was to have a brighter light, I would have more photons hitting per second, but my electrons would still have exactly the same amount of kinetic energy. The kinetic energy is directly proportional to the frequency of the light or the wavelength of the light. It is not proportional to the intensity of the light. So the intensity of the light just determines how many electrons are given off per second. Now we say because of this idea that light has a wave-particle duality. So we know that light can cause diffraction and constructively interfere to make bright spots when we diffract it. Now, because light can diffract, we would say it behaves as a wave. But in this instance, if light was truly just a wave, we would expect that when we increase the intensity, we would have more energy. So a more intense beam of light should produce electrons with more kinetic energy, but it doesn't. If we use a more intense beam of light, we just get more electrons. They have the same amount of energy. Therefore, light doesn't behave as a wave in this instance. In this instance, it behaves as a particle. You can think about it this way. If I have a beach made of pebbles, okay, so there's a beach and it's constructed of lots of pebbles about the size of your palm. If I was, I guess those are stones more than pebbles. If I was to throw a stone about the size of your thumbnail at those, it wouldn't have enough energy to dislodge one of the palm-sized stones. So that would be like a photon with a low frequency. However, if I was to take another palm-sized stone and throw it at the beach, it would be able to dislodge one of those bigger stones. That's like a light with a higher frequency. Now, in this case, my light is acting like a particle, like a stone. So light has a wave-particle duality. Right, so we can construct a circuit with this photoelectric cell, an ammeter, and a voltmeter. Now, one of the problems with the photoelectric cell is it's very hard to measure the voltage of a photoelectric cell because it doesn't produce a very high current. Now, the way that we can measure its voltage is we can have a photoelectric cell and we can shine light on it, and we can produce a voltmeter, or we can place a voltmeter in series, sorry, not a voltmeter, this is a power supply with a voltmeter across it, in series to this photoelectric cell. Now, when we change the voltage on this power supply, and then we measure what the voltage is, when we change it, and if we change the voltage enough and the voltage is pushing against, okay, so here's what the voltage is going this way, yeah, voltage is pushing against the voltage that's produced by the photoelectric cell. When these two voltages are equal, we get zero current. So as soon as we measure zero current, we write down what the voltage was when it pushed against the photoelectric cell. That voltage there is equal to the voltage of the photoelectric cell. This is called the cutoff voltage. This is the voltage that stops the photoelectric cell from producing a current. Now, we can use this cutoff voltage to find the kinetic energy, because the kinetic energy of a particle just equals the cutoff voltage times the charge of an electron. Okay, so we can work out the energy of a photon by using Planck's equation. And we use Planck's constant here. So basically the energy of a photon of light is equal to the Planck's constant times its frequency. So if we're given the wavelength, like what I have on the left here, 400 nanometers, I can find the frequency first, and then I can find the energy by using Planck's constant times the frequency. Or I can combine these two together to get this equation to find the answer. So I do that here, and my answer for my energy for this 400 nanometer photon is 4.936 times 10 to the negative 19 joules. Work function. So that is the energy of a photon. Now, if you think about a photon is the light particle that hits the surface of the emitter and bounces the electron off. The amount of kinetic energy the electron has must be less than the energy the photon has. But the energy of the photon is used to dislodge the electron. And some of the photon's energy is used to dislodge the electron, and some goes to the kinetic energy. The energy used to dislodge the electron is called the work function. Now we can calculate the work function. Well, we can use this equation on the left here. So the first thing to calculate the work function is to calculate the kinetic energy of the electron. So the kinetic energy electron, of course, equals the charge of an electron times the voltage. So for this example up here, voltage of 6.25, this is our stop-in voltage, or our cutoff voltage. We multiply it by the charge of the electron, and we find the kinetic energy. Now, if I now find the energy that the photon had for a start, and let's go back. Here's the energy the photon had for a start, HF, and I subtract the kinetic energy away, I can get the work function. In this case, the work function is 1.26 times 10 to the negative 19 joules. So what I did here is I took this equation, and to find the work function, I just rearranged it. So I took work function to the other side, made it positive, and took EK to this side, made it negative. So the work function equals the energy of the photon minus the kinetic energy. I can plot the frequency of the incident light against the kinetic energy for any frequency. For any emitter surface. So for different metals, they have different lines, and I can get a graph. So this is a graph of, let's say, a metal. It could be iron, and I've plotted different frequencies, and then I've calculated how much energy each frequency has had, and then I've plotted the line of the data. Now, where the point, where the kinetic energy equals 0, this is our threshold frequency, because remember, when a photon ejects an electron, but if an electron had no energy when it was ejected, the energy of the photon must be equal to the energy it took to eject it, which is the work function energy. So at this point, when y equals 0, this is our threshold frequency. The y-intercept down the bottom here is our work function. It's actually the negative of our work function because it's below the 0 here. But if we just, and we can see here from this from the graph equation, y equals mx plus c equates to this work function equation, the kinetic energy equals hf minus work function. So work function is c, or the negative of c. That means that the x must be frequency, which it is, ek is y, but the gradient of this line is actually Planck's constant. And we notice if we draw this line for different metals, so here it is for two different metals, here's zinc, here's gold, they are parallel lines because they both have the same constant. They both have Planck's constant. That never changes, so the lines are always parallel. What changes though is the amount of energy that's needed to eject an electron, and each one of these have a different work function. And we can see here that zinc has a smaller work function than gold does. Okay, that's the end of this video on the photoelectric effect, and I hope that's been helpful.